Welcome back, Focus Learners. Today on The Explainer, we're doing something, well, honestly, absolutely incredibly exciting. We're taking these dense, totally authentic radio frequency engineering field notes, and we're going to translate them into a clear, highly visual guide so we can understand exactly how 4G LTE networks actually operate. Basically, our goal today is to bridge that gap between invisible physics and the boots-on-the-ground testing that keeps your mobile data flowing. Let's get right into it.
Okay, let's dive into this. Here is our roadmap for today. We've got 5 main building blocks. 1, frequency basics and resource blocks. 2, throughput calculations and signal quality. 3, MIMO technologies and modulation types. 4, voice services with CSFB and Volte. And finally, 5, field testing protocols.
And here is our foundation. Throughout this whole explainer, we're going to be deciphering these actual handwritten engineering logs, these complex formulas, the acronyms, the sketches. They aren't just textbook theory. No, this is the raw data that field engineers use literally every single day to optimize the networks that you and I rely on. So let's start decoding this stuff. Section 1. Frequency Basics and Resource Blocks. Organizing the airwaves. So LTE networks operate on specific frequency bands, right? We're talking mostly about the 700, 900, 1800, 2100, and 2600 megahertz bands. But here's the really cool part. The network handles traffic on these bands completely differently depending on which way the data is flowing. For your downlink, like when you're streaming a video from the cell tower, LTE uses OFDMA. That's orthogonal frequency division multiple access. It's a mouthful, I know, but it basically allows multiple users to share the bandwidth super efficiently without stepping on each other's toes. But then, for the uplink, when your phone is sending, say, a photo back to the tower, it switches to SCFDMA, or single carrier frequency division multiple access. Why? Well, this single carrier method is specifically designed to be way more power efficient, and that is exactly what saves your phone's battery life. Pretty smart, right?
Now, if you think of network bandwidth as a massive highway, resource blocks, or RBs, well, those are the lanes. According to the field notes, one resource block is made up of exactly 12 subcarriers, each 15 kilohertz wide, and they're transmitted over a tiny time domain of just 0.5 milliseconds containing 7 symbols. Okay, a lot of numbers there, but the golden rule to remember here? For every 1 megahertz of bandwidth, the network gives us exactly 5 of these resource block lanes.
Section 2, Throughput Calculations and Signal Quality. Measuring data flow. So how do we actually measure the flow of data through those newly established highway lanes? Well, it all starts with power. RSRP stands for Reference Signal Received Power. To put it in plain English, this is just the raw strength of the connection between your phone and the cell tower. It's measured in decibels, and it ranges from an amazingly strong negative 44 dB all the way down to a practically dead zone level of negative 140 dB. And as you'd probably guess, this metric is heavily affected by physical distance and structural blocks. Think, being far away or stuck behind thick concrete walls. But here's the thing. Power definitely isn't everything. I mean, you can have a super loud signal, but if everyone else in the room is yelling at the same time, you still can't understand a word, right? That's exactly where SINR comes in, signal to interference plus noise ratio. Ranging from 0 to 30, SINR is all about measuring signal clarity. As our source notes reveal, even if you have crazy strong power, interference from overlapping cell sectors or signals that are just overshooting their intended range, well, that can completely ruin your data flow. Now, when engineers sit down to calculate total throughput, which is basically your final megabits per second speed, they look at an equation that's split into constants and variables. The constants, those are just fixed physics. We always have our 12 subcarriers, our 7 symbols, and that 0.5 millisecond time slot. But to actually boost your speeds, engineers have to actively manipulate the variables. They can increase the number of resource blocks, upgrade the MIMO antennas, or change the modulation type. Moving right along to Section 3, MIMO technologies and modulation types. Maximizing data flow. To see exactly how those variables work in the real world, we first have to look at transmission modes within a multiple input, multiple output, or MIMO system. The field notes highlight 2 really distinct modes here. First, TM3. This is an open-loop feedback system. It relies on 2 antennas and 2 signals, and it's heavily utilized when you're moving fast, like bombing down the highway, where there is just literally no time for constant feedback back and forth. On the flip side, we have TM4, which is a closed-loop system. Used in highly congested areas, TM4 is constantly sending a pre-coding matrix indicator, a PMI, back to the tower. This allows the network to precisely adjust the phase of the signal for maximum efficiency. It's like having a traffic cop constantly optimizing the flow. And the next big variable engineers tweak is modulation. You can think of modulation as how tightly we can pack cars into our highway lanes. As your radio conditions improve, the network actually upgrades your modulation on the fly. We start at QPSK, which packs 2 bits of data per symbol. But if that SINR clarity gets better, boom, we step up to 16 QAM, packing 4 bits, then 64 QAM, packing 6 bits. And it scales all the way up to 256 QAM, which incredibly packs 8 bits of data per single symbol, vastly increasing your download speeds. It's a real game changer.
Section 4, Voice Services, CSFB and Volte, handling standard calls.
Okay, let's shift gears for a second. How exactly does a 4G data architecture handle a regular old standard phone call? Well, historically, 4G was built purely for data. So back in the day, when a call came in, the network used CSFB, Circuit Switched Fallback. This literally forces your phone's connection to drop all the way down to the legacy 3G network just to take the call. It uses this process called blind redirection, and honestly, it takes a few seconds to even connect. But today we use VoLTE, or Voice over LTE. This treats your voice call as just another high-speed data packet, which keeps you seamlessly connected right there on the 4G network. So the crucial point here, and this is a really important number from the notes, is minus 111 decibels. Let's say you're on a crystal clear Volte call, right? But you drive a bit too far away from the tower, and your RSRP power starts dropping. Right at that exact minus 111 dB threshold, the network kicks into gear and triggers something called SRVCC, which stands for Single Radio Voice Call Continuity. It seamlessly hands your active 4G call back down to the 3G network right before the signal completely drops out. It literally saves your conversation from just hanging up on you. Finally, Section 5, Field Testing Protocols. Taking it to the real world. So how do engineers take all this theory out into the real world to hunt down customer network complaints? Well, they utilize some very strict, standardized testing protocols, which they divide into 2 main buckets, statics and dynamics. Static tests, as you might guess, are performed while completely stationary. Engineers will lock the phone to specific frequencies and run pure download, upload, ping, and speed tests just to gauge the raw baseline performance. But dynamic tests, those involve movement. They do download and upload turns while physically driving around to see how the towers hand off the signal. They also test carrier aggregation out there, ensuring the phone can successfully combine multiple bands, like pulling from both the 700 and 1800 megahertz bands while on the move. And honestly, looking at this logbook reveals just how meticulous this entire process is. This specific entry we're looking at shows an indoor pinpoint test. The field engineer literally has to walk to 30 specific physical locations inside a single building, and at every single pinpoint, they execute a whole series of stress tests. We're talking logging 20 static CSFB calls, running network speed tests, and taking snapshots of the RF environment to figure out exactly where and why the signal dies inside that specific structure. Talk about a giant puzzle. Which brings us to our final thought for this explainer. The next time you load a seamless 4K video while sitting inside some massive concrete building, or your phone magically manages not to drop a really important call as you drive down the highway, maybe take a second to ask yourself, how exactly are all these invisible metrics operating around me? Because, it's not magic at all. It's a brilliant, perfectly mathematically orchestrated symphony of resource blocks, SINR clarity, and flawlessly timed handovers. All of it designed by the very engineers behind these fascinating notes. Thanks so much for joining me on this explainer, and as always, stay curious.